Triaxial compression test covers the determination of strength and stress-strain relationships of a cylindrical specimen of either an intact or reconstituted soil. For different engineering requirements, the condition of compression test may be chosen from consolidated undrained, unconsolidated undrained, and consolidated drained. At least 3 specimens are required for tests at different chamber pressures. If it is difficult to obtain enough specimens for a group test, the triaxial compression test with multi-stage chamber pressures should be conducted. These methods are applicable for fine-grained soils and coarse-grained soils finer than 20 millimeters. Parameters to be measured are the maximum principal stress and axial deformation. Apparatus. Strain-controlled triaxial apparatus includes axial loading device. The load cell shall be chosen according to the strength of sample. The accuracy of load cell shall be within 1% of its full capacity. Chamber pressure system with an accuracy of less than 1% of its range. The piston passing through the top of the chamber and its seal must be designed so the axial load due to friction shall be negligible. Back pressure system. Pore pressure measurement system. The coefficient of volume change shall be less than 1.5 into 10 raised to the power minus 5 cubic centimeter per kilopascal during the process of exhausting. Volume change measurement device. Balance. Type 1 with a capacity of 200 grams, readable to 0.01 grams. Type 2 with a capacity of 1,000 grams, readable to 0.1 grams. Rubber membrane shall be elastic latex membranes. The membrane thickness shall be in the range from 0.1 to 0.2 millimeters for specimen with diameter of 39.1 millimeter or 61.8 millimeter, or in the range of 0.2 to 0.3 millimeter for specimen with diameter of 101 millimeters. The flaws, pinholes, and leaks of membranes shall be inspected before using. Porous discs, diameter shall be equal to that of the specimen. The coefficient of permeability of the discs shall be greater than the specimen. The discs shall be soaked in water before using. Vacuum saturation device includes a vacuum pump, a pressure gauge, a vacuum container, and a split funnel. Other apparatus. Rammer. Saturator, separator of undisturbed soil. Soil lathe, membrane expander, and split mold. Specimen requirements. The chamber pressure shall be determined by the engineering conditions. The diameter of specimen shall be in the range of 35 to 101 millimeters. For specimens with cracks, structure plane, and weak surfaces, the diameter shall be greater than 60 millimeters. The height to diameter ratio shall be between 2 and 2.5. The dimensions of specimen shall meet the requirements enumerated in the table. Step 1. Specimen preparation and saturation. For undisturbed specimens, cut a specimen with a diameter slightly larger than the required specimen by a wire saw or steel straight edge. Then put the specimen on a soil lathe and trim the specimen vertically to the final diameter with a wire saw or steel straight edge. Remove the specimen, cut the specimen to the final height. Where the voids appeared, carefully fill the voids with the trimmings. Weigh the final specimen. Determine the moisture content of sample obtained from the trimmings. Emery wire cutting machine may be used to trim the original specimen to the required diameter. For disturbed specimens, add water to produce the desired moisture content. The specimen shall be reconstituted to the desired density. Specimen may be saturated by vacuum pump, water head, and back pressure method in accordance with the type of soil and desired saturation degree. Vacuum saturation method. Successively insert porous disc, filter paper. Mold with a specimen. top filter paper, top porous disc, and top plate into the saturator and tighten the assembled device. Put the saturator with specimen in a vacuum container. Coat a thin layer of Vaseline on the contact area between the container and its lid. Install the split funnel and connect the vacuum container to the pump. Start the pump. When the vacuum pressure is close to the atmospheric pressure, add water in the split funnel and open the clamp to allow water to flow into the vacuum container slowly. The vacuum pressure shall be constant during the procedure. Stop the pump until the saturator is submerged. Open the clamp to let air go into the cylinder. Stand for a while to enable the specimen fully saturated. Stand 10 hours for fine-grained soil. Open the vacuum container. Take out the saturator and remove the specimen with the mold. Weigh the total mass of the specimen and mold. Calculate the degree of saturation in accordance with the formula. If degree of saturation is lower than 95%, the pumping process shall be continued. For water head saturation method, the water head at the bottom of specimen shall be higher than the top about 1 meter. Allow the water to percolate from the bottom to the top of the specimen. When the specimen could not be saturated completely by pump or water head, back pressure should be applied to the specimen in the test. For back pressure saturation method, after the sample is installed in the chamber, apply chamber pressure and back pressure in stages at the same time. When the ratio of pore pressure to chamber pressure increment is greater than 0.98, the specimen is considered to be saturated. If the initial saturation degree of the specimen is low, the pumping saturation shall be prior to the back pressure saturation. For the preparation of sandy specimens, directly fill the membrane with specimen by layers at the base of chamber. For the saturation of sandy specimens, a proper amount of pure water should be added prior to filling the membrane with the boiled specimen. Step 2. Exhaustion of apparatus. The air in the system shall be forced out completely by flushing with distilled water or applying pressure to dissolve the air in water and then overflowing from the pedestal. Step 3. Mounting specimen. Put porous disc, soaked filter paper, on the chamber pedestal successively. Put specimen, soaked filter paper and porous disc. Cover the specimen periphery with 7 to 9 filter paper trips. Sheathe the rubber membrane around the specimen with the membrane expander. Roll the membrane on the base and seal it with elastic band or O-ring and remove the expander. Open the pore pressure valve. Allow the water to flow through the specimen from the bottom. Remove the air pockets from between membrane and the specimen by light stroking upwards. Close the pore pressure valve. Open the drainage valve to moisten the top cap. Fit the cap onto the porous disc. Roll the membrane on the cap and seal it with elastic band. Remove surplus water between the cap and the membrane. Close the drainage valve. Assemble the triaxial chamber and bring the load piston into contact with the specimen cap. Align the piston and the specimen cap. Tighten the bolts on the base of the chamber. Rise the base of the chamber until the reading of the load indicator changes slightly. Open the vent screw on the chamber and the chamber pressure valve. Fill the chamber with water, ensuring that water fills the chamber and overflows from the bleed plug. Close the chamber pressure valve and tighten the bleed plug. Step 4. Consolidation. Select CU test and input the parameters. Adjust the drainage barrette to make the water level align with the center of the specimen, and record the reading of water level in the drainage barrette before the specimen is consolidated. Apply chamber pressure to the specimen to desired value. The chamber pressure should be determined according to the actual stress of the engineering. Record the reading of pore pressure. When the pore pressure rises to the chamber pressure, open the drainage valve and start the process of consolidation. Draw a plot of pore pressure versus square root of time, and a pore pressure versus log time. Allow consolidation to continue until the excess pore pressure dissipates at least 95%. Close the drainage valve after the consolidation is finished. Record the reading of the drainage barrette. The amount of consolidated drainage is the change of amount of water in the drainage barrette before and after consolidation. Step 5. Specimen shearing. Adjust the pedestal of the sample chamber slightly to allow the piston to contact with the specimen cap to permit proper seating load. Apply axial load, input the amount of drained water during consolidation, and start shearing. The shear strain rate of clay should be 0.05% to 0.1% per minute for clay, and 0.1% to 0.5% per minute for silt. Observe and record the change of curve and specimen during the shear process. Continue the loading to 15 to 20% strain. Step 6. Unload chamber pressure. Open the chamber pressure valve and loosen the vent screw. Then drain the water in the sample chamber. Low down the chamber to allow the load cell separate from the load piston. Remove the chamber and specimen quickly. Describe the failure specimen. Determine the moisture content of total specimen. Step 7. Calculating and plotting. Calculate the height and sectional area after consolidation. Calculate the axial strain and the corrected sectional area of the specimen. Calculate the deviator stress according to the axial load and the corrected sectional area of the specimen. Calculate the effective principal stress ratio according to the formulas. Calculate the initial pore pressure coefficient and the pore pressure coefficient at failure. Plot a graph of the deviator against axial strain. Plot a graph of the effective principal stress ratio against axial strain. Plot a graph of the pore pressure against axial strain. Plot effective stress path curve. Calculate the angle of shearing resistance and the cohesion intercept in terms of effective stress according to the inclination and intercept of the failure envelope. Failure point is defined by the peak of deviator stress or effective principal stress ratio. If there is no peak, failure point is defined by the dense parts of effective stress path or the value of deviator stress at an axial strain of 15%. Plot Mohr circles in terms of total stress with its center of P and its radius of Q under different chamber pressure, and plot the corresponding failure envelopes. Derive the total stress strength parameters. The angle of shear resistance and the effective cohesion shall be determined by Mohr circles in terms of effective stress with its center of P' and its radius of Q'. It should be noted that 1. The test shall be carried out under a constant temperature. 2. When determining the stress-strain relation of soil, 2 circular membranes with silicon grease inside shall be placed between the specimen and the porous plate, and a hole with a diameter of 1 centimeter shall be left in the middle of the membrane to drain. This is the end of the test. For more information, please refer to the main references.